In this video, I will discuss the energy analysis of a steady flow process. So, a steady flow process, you know the definition of the steady flow process. A steady means it's not related with time. So that means no change of the fluid flow in a controlled volume with time. So you can see the definition here. A process during which a fluid flows through a controlled volume steadily. So that means, in other words, you can say no change with time. So in our practical life, you can see this example here, especially the power plants. Not only the power plants, the compressors and the nozzles, turbines, and many more engineering applications. They need to operate, they need to run for a long period of time with the same setup, uniform setup. So what actually happened is, initially, at the very beginning, during the startup, it is transient, and after some times, once the transient process completed, then it becomes steady operating conditions, and then it run for a long time. It's kind of like this. Let's say you have a pipe flow. So the flow, initially it has uniform velocity. After some distance, the flow becomes fully developed, and then if, let's say, this is 10 meter, if the pipe is, let's say, 1000 meter, then after 10 meter, so initially it was developing, and it is fully developed here, and then after this 10 meter, remaining 990 meter, the flow will be fully developed. So initially it is kind of transient, and then it becomes steady. So for most of the engineering process, actually, once the transient startup is completed, then it becomes steady operating condition, and it's flow for a long time this way. So this sort of device is called a steady flow device, and the process is called the steady flow process. So in general, during the steady flow process, there will be no inside the control volume, the fluid flow will remain constant, so it will be steady, it will be uniform. So which means there should be no extensive change of the properties inside the control volume. So if you look here, guys, this is the dotted line, it is the control volume. So under steady conditions, we have the inlet, we have the outlet. So mass is coming, mass is going out, and inside this control volume, the total mass remains constant. So that means you can see the mcv is constant, ecv is constant. And in this case, actually, as it is a steady condition, so boundary work is 0. So we can say the boundary work is 0 for this problem, and the mcv constant. That means the change of mass inside the control volume is constant, change of energy inside the control volume, it is constant. So this is actually the general definition of the steady flow process. So we said a steady flow device, that kind of device, engineering device, which to run with the same or uniform operating conditions for a long time, and the process is called the steady flow process. So now we will discuss actually the energy analysis. What is happening? So during the steady process, we said the mass in and mass out, it is constant, it is same, it is uniform. So maybe then what we can write, guys, so the mass and the energy balance. So what will be the mass balance? It will be the m in and m out. Now we need to actually use this summation sign, because we can get many problems that could have multiple inlets and multiple outlets. So if we have a system like this, let's say we have 2 inlet and 1 outlet. So this is in, and this is out. So that means then we need to include 2 inlet here. We need to just add these 2. So that's why we just put summation. But we'll try to analyze this mass and energy balance for a single stream. If we have in real life a multiple stream, then we'll just add it, that's it. But to avoid the complexity, we will consider we have a single stream. So we'll eliminate this term, and it will be the mass in equal the mass out, right? So we know the definition of the mass flow rate. The mass flow rate definition, we know it is actually the density, velocity, and the area. I put it is 1. rho on b on a1. Let's say this process we have actually one inlet, we said we have one, so this is actually the the process 1. Let's say this is process 2. So for this section we said rho on b on a1. For outlet we say rho to v to a2. So here this one is actually telling the inlet, this 2 is the outlet. So as it is the steady flow process and we have the control volume here, so we have the control volume here, Cv. So we said we agreed that the mass change, it is constant here, the energy change, it is constant here. So we can write the energy change in control volume, what it is, ECV. This is equal constant. The energy inside the control volume is constant, right? So yeah, the control volume, so we should say it is the energy in the control volume. So if we consider now energy change in the control volume, when it is changed, then we'll write delta E Cv. What it will be, guys? It will be 0 in real life. So far I discussed the mass balance. So now if I write down the energy balance, what it will be? The energy balance, we know the formula, the energy in, the energy out, it is equal delta E over delta T. And this is actually the system. This energy, guys, it could be the net energy, the rate of net energy, it could be the work, heat or mass. There are 3 forms of energy. The heat energy, work energy and mass energy. I'm just not writing a lot here. You already know this energy balance relations. So when it is a steady condition, then the energy change inside this control volume, it is 0, right? Because no change with time. So what we can write, the energy in, it is equal energy out equal 0, right? We can write that, yes. Or we can write the energy in, it is equal the energy out. So as we know, this energy in or energy out, it could be 3 different forms: the heat, work or mass. So can we write it like this? Let me go back to the next slide and it should be much better. So I can write the energy in, it is equal energy out. So the energy in, it could be the heat energy. So let's say heat in, we said the work energy and the mass energy. And for energy out, it could be same, the heat energy, the work energy and the mass energy. This is out, this is in. Look, some of you already know this is actually the mass energy. We discussed during the lecture what is the mass energy. The energy transport by mass is you need to just multiply the mass with the total energy. When we have a flowing fluid, we already calculated theta. So if you calculate, if you multiply mass with the the energy, total energy for a flowing fluid, then we will get the energy transport by mass. So here it is actually that term, the energy transport by mass. So for your better understanding, what I can write it down, this is actually the heat energy, this is the work energy and this is the mass energy. Now guys, for flowing fluid, can you remember what was the mass energy? What is the total energy? Theta, it was H's v square over 2 and g z. So if we calculate the mass energy, then we need to multiply m dot here. That's it. So what we will write, we can write, so this is actually the m theta. So we can write it like this: the Q in, the W in, plus the sum of m H's v square over 2 gz. This is equal Q out, W out, plus sum of m. Here we'll put it right out, we'll write it as in, so then it is H's v square over 2 and gz. So this is actually the the energy balance, especially when we are discussing for a flowing fluid or a steady flow system, the energy analysis for the steady flow system. So this is the general expression we need to use. There are some other conditions where sometimes we have this unknown heat or work interactions and we don't know the direction as well. So if we have some similar cases, then you just go through the books, you will get some problem where the heat interactions and the work interaction, it is unknown. Then there is an equation and we will use that one. So during the lecture I will discuss that one. So here what I did, guys, when it is the mass balance, mass in, mass out, energy balance, energy in, energy out, and the change energy, it is 0, then we could have different types of energy. So I just write down here the heat, work, and mass energy. So this is actually the final equation we may need to use to solve some problems. But definitely depending on the problem, we will simplify this equation and it will be much clearer. This is just for the demonstration purpose. Maybe you do not need to use this expression directly to solve some technical problems, but if some of you are interested to know actually this expression, that's why I made this video. But during the lecture I will discuss how we will simplify this and how we will solve problem by using this equation. So that's it.